I hope so.
Right. Good morning, everyone. Thank you so much for coming to the seminar this morning. It's my great pleasure to introduce Dr. Anton Oliynyk. The pronunciation
Very
is
nice.
very
Yeah.
close.
Yes, very close.
Anton is originally from Ukraine, associate at the University of Alberta. I believe he did his PhD and also postdoc in Arthur Marr's group there, solid state chemist, crystallographer. We're really interested to learn about some of these buzzwords we've been hearing wherever you go about machine learning. So what the heck is machine learning and how can we apply this to certain applications? Accelerate the discovery of materials. And then we have a couple special treats for you this week. I'd like to invite you, or you can talk to me about it. We have 15 people about registered. Tomorrow we're going to have a small short course on actually how to implement practical machine learning applications in your science. You could come and practice in using some of these codes to do machine learning. And then on Wednesday, that's at 1 p.m. in the ACC. At Wednesday, our own Li Zhu is going to give us a little brief seminar on another form of artificial intelligence, which is crystal structure creation. So let me know if you would like to join us. So without further adu, please join me in welcoming Anton.
Thanks. Thank you, Tim, for the introduction. I hope you hear me right. The microphone is working. Very nice. OK, so as Tim mentioned, I did my PhD also in Canada at University of Alberta. I started my PhD working on intermetallics, more specifically germanides. But later, probably like 3 years in PhD, I just decided to try some new tools to help me to discover materials in an efficient way to reduce the cost risk and other time risks and so on. So after my PhD, I moved to University of Houston, where I also applied machine learning tools as a postdoctoral researcher. And after that, I'm back to University of Alberta as a research associate. So right now, I'm trying to give you an introduction to machine learning. There will be probably a very brief intro to that, everything that you need to know about machine learning as a PI. After that, we'll go through a couple of case studies. And I will reveal all my secrets tomorrow how to do machine learning during our workshop and try to demystify machine learning in general. And as Tim mentioned, it's sort of a buzzword right now. OK, so you can use machine learning for various applications. Here, just like a short overview what might be used for. If you're using Google, Facebook, YouTube, you produce a lot of data every day, and you can be sure that your data is used for the right purpose for ad companies. So they already know your interests. Also, it can be used for character recognitions, for filtering your spam messages, and so on and so forth. So companies are using our data every day. So the idea is, why don't we use data that we have about materials to make sure that we use it to develop new materials faster? OK, so one more specific slide about applications here. Character recognition is one of the applications. If you use tablet and you write handwritten text and somehow it's magically converted into digital text, you're using machine learning. You're using machine learning every day when you open your email inbox. So you probably notice that you get less and less spam messages every day, and we need to thank to machine learning. OK, language translation is another cool application. If you were using like online translation a couple of years ago, you probably noticed that translation back then wasn't that great. It's simply because the translation was word by word. Right now, we don't use word-by-word translation, especially Google Translate. It's simply vector-to-vector translation. So the text is transformed into an encoded sentence, which is basically vectors, and then translated back to another language. So we had a better translation in terms of like meaning-by-meaning translation. It really helps when you have to translate like idioms. or some common expressions. Okay, another cool application of machine learning that our engineering colleagues have been using for years now is optimization. For example, here is a metal piece that is used for bridge construction. And there is like the same piece, but with 75 mass reduction here. So you save on materials if you use this application. Specifically, this one is an example of optimization. Plus, I really like to show this slide because it clearly shows that machine learning is also can help you to create a piece of art, because you can see the metal piece on the right looks way more beautiful than a human-made piece. Okay, it all started not so long time ago. In 2011, there was a program launched, which is the Materials Genome Initiative. The idea behind that is that we can develop materials faster. And here, the President Obama just mentioned something about developing iPods and iPads. Many things have changed since then because iPod is not produced anymore and so on. But the idea is clear. We need to search for materials faster so that it will help us to develop technology. So many researchers have responded to this call, the Materials Genome Initiative, and part of the research that I will be presenting today is also my response to this call about developing materials faster. If you think about materials and how we search them, there are definitely many ways to do that. One of them is not probably very scientific way. It's called a serendipitous discovery. So, and as a researchers, we probably don't believe in that so much, but in fact, we use materials that were discovered serendipitously. For example, like neodymium iron boride magnet, the strongest ferromagnet that exists right now at room temperature. So it was found like a way before it was patented as a magnet. So it was also discovered serendipitously. So the people that were picking up crystals of this compound just noticed that it just sticks to needle just like crazy. So, and that's how they discovered this material. So in general, it's like hunting for a needle in a haystack. Actually, some people try to do it, not so successfully for sure. And if we just want to keep the same analogy here, searching with machine learning would be a smarter way to find materials, like using metal detector to find a metal object in a haystack. So we can think about it as reducing time risks and definitely money risks when you explore new systems, especially in a chemical white space. So about buzzwords, you probably recognize some of them. The biggest one probably is AI, artificial intelligence. This is not my figure, but it illustrates very well the overlap of areas. So make sure that if you do data mining, you probably do some sort of statistics, of course. If you do statistics, you probably also do some sort of pattern recognition. And pay attention here, the statistics never overlap with machine learning here, which is a good way to understand the difference between them. So we collect data, we put it together, we made some statistics out of it. We can also recognize some patterns. But with statistics, we just make some conclusions as researcher. And machine learning helps to make conclusions as machine thinks. A machine can guide you towards like new interesting areas of materials that you are studying. So in machine learning, machine makes the decision. And in statistics, it's mainly researchers who make decision. And by the way, don't be confused by data mining. Data mining is probably you're doing it every day in your research. It's basically reading papers, summarizing information, and writing introduction about your area. That's what we call data mining. And there are also some terms that are very similar in terms of meaning for machine learning and statistics. Some people just try to avoid calling machine learning. They prefer term statistics because it's kind of true. You work on statistics, but the actual decision machine is making in the very end for machine learning. So some of the terms like learning and fitting is almost the same. They mean almost the same. So typical problems in machine learning are illustrated here. we usually organize the data in a way that we have y vector, our response or class. For example, if I want to predict electrical conductivity, I will have electrical conductivity values in my y vector. If I want to predict class of materials, if it is semiconductor or metal, that also will be my y vector, semiconductor or metal. And x is our variables. There are different terms that mean almost the same, like variables, descriptors, features. It simply depends on the area that you come from. So some people that work with statistics prefer variables. Some people who work with machine learning would prefer features. But they are sort of like interchangeable. You can use like either word. These are the parameters about our materials. In chemistry, for example, we can use like electronegativity as x vector. We can use size of atoms as x vector. We can use anything else, like number of electrons. They also might be a parameter. So all this information about material we just put in our x block. The problems can be classification or regression. That's the typical problems. The only difference between them is y is an integer in classification. In other words, you can think about it yes/no response. Like for the question, is my material semiconductor? You can have a response yes/no. That will be classification problem. For the regression, you will have like any values in between for y. If you're measuring electrical conductivity, that will be your electrical conductivity value. What we're trying to do, we try to correlate our x vector with y. This is basically what machine learning is. You input information x here, and you try to predict what would be the y response. The typical scheme for analysis with machine learning looks like this. We start with database that we compile. We can use our lab data, and it's very common, especially for small institutions. They try to make use of their old data that they were recording in their lab books by hand. Now they're converting it into digital format that they can use the same data that they have been collecting for decades for machine learning application. Or databases, you can purchase them for sure. Database, it might be something that you compile from the review papers that you read and so on. Variables, I already explained it to you. It's like the properties that describe materials. Machine learning model we create, and then we do prediction. However, it's not that simple. If it was that simple, half of people that work in machine learning wouldn't have jobs right now. If it was that simple, we would significantly advance our technology, and by now we would have like flying cars, and self-driving cars would be like very common everyday technologies that we see on the roads. But there is a problem to that. The first problem, like we cannot trust every data that we put into our model. So data sanitizing is required simply because not all the data is reliable. So when you read a paper, there's definitely, sometimes there are typos, sometimes even some researchers put on purpose some unreliable data. It's quite common, and yeah, thanks for laughing on that, but with machine learning, actually it's funny, but with machine learning we can easily identify groups that misuse our trust and basically publish some unreliable data. So we can cluster these groups and just mark them as unreliable with machine learning. It happens, so sorry to say that, but it also happens sometimes. Also, variables can be not, I wouldn't say trusted, but in terms of it, not all the variables are important. If we put too much information of our model, it can introduce a lot of noise, and noise is a huge problem, actually. It can reduce the accuracy of our models. That's why variables need to have what we call feature selection. Try to think about feature selection as a statement that not all the opinions are important. Not all the opinions are equally important. So sometimes the data that we put in, we just simply need to ignore in order to make a better use of our model. Model validation, something that I will explain more on the next slide, but we need to make sure that we created a model that can be reproducible and that can produce us very nice results and reliable real-world results. And prediction also requires experimental validation. Experimental validation is a huge issue right now because doing machine learning is relatively simple in terms of like using software. Many people can do, and every day we have like exponential growth of publications that use machine learning. However, it's very important to experimentally validate your prediction. There is absolutely no need to have a prediction if you can't validate it in your lab. So that is my philosophy, actually. So every time I do prediction, I need to make sure that we can validate it experimentally. Otherwise, it won't be published at all. So let's talk a little bit more about model validation. What do I mean? Because every other steps and roadblocks, potential roadblocks I have explained, and probably you intuitively understand, but what is like model validation step? So for example, if we have a problem, we need to segregate these red points from blue points. Well, we can create a very accurate model, but it will not be very realistic. For example, if you look at this green line here, it outlines every sample very nicely, and it is basically a model that has 100% accuracy. In other words, we can force that machine to give you the best model, like the best answer, but it's not going to be helpful in real world. In real world, the black line would be probably the best solution in separating these two classes. Another example for regression model, if you want to find a correlation between X and Y, and the straight line would be the best solution here. But if you force your model to perform its best, right, you will probably get something like this blue line, which looks exactly 100% accuracy, but it's not applicable to real life discoveries. Okay, so to avoid these problems, in machine learning, we use a split of training set and validation set. Ideally, informatics people prefer 50-50% split, so half of the data is used for training, half of the data used for validation. Think about companies as Amazon and Facebook. They have millions of data, like more than millions for sure, and it's generating and generating more and more data by users every day. And they have that privilege of using 50-50% split for training and validation. But in material science, we are lucky to have like 100 data points. So that's why split 2/3, 1/3 would work quite well. This is typical graph for machine learning classification. Here is Y vector prediction for binary problem. If it is like class 1, it has a probability close to 1. If it's not class 1, it has probability close to 0. TP means true positive response. So here we try to classify red circles versus not red circles. So that's why we have true response close to 100% probability for red circles in training and validation, and true negative response for all other classes. Here is the decision barrier, which is not always 50% in binary problem. And there are also some characteristics, some parameters of machine learning model. We can call it sensitivity, specificity, and accuracy. Sometimes model performs very well on correctly identifying if compound is class 1, and in other case, if it calls everything class 1, it's not helpful model. That's why we need to make sure that we have also true negative predictions. This is parameter for specificity. And accuracy, probably like a general statistical parameter of our model. Let me just briefly to introduce you the methods that people use in machine learning, specifically for materials domain. I will just try to give you like intuitive understanding of these methods, so no math is involved here at all right now. One of the methods is called partial square discriminant analysis. If we have two-class problem, you have like red circles, blue circles, you want to separate them somehow, and you want to draw the boundary. So for us as human beings, it's a very easy problem. We can draw a line right now, right? So there is no issue. But for a machine, it's not that easy. So what do we try to do first? We try to set a new axis. So one of the axes will correspond to the highest spread of variance between the data. And the second axis, that should be orthogonal to the first one, should be selected the way that it separates the classes the best way. Once we have this new axis, we can create clusters of points. We expand these clusters until they touch each other, and that's how we make a model. So this model tells us, oh, if we have a new sample for example, somewhere here, would it belong to red class or blue class? Probably there's high probability that it will belong to the red class. Another method is very common in chemistry, and probably 90% of papers will use this method. It's called support vector machine. It's a very mathematical term. Don't be scared of it. So the idea is that we have the same set of data, and we can set a line that probably will correspond to the best segregation of these two classes. And what we do when we set a line, we try to expand its boundaries until it touches the samples. And the most important samples in this case are these samples at the boundaries that are called support vectors. So our model is built not on the whole array of the data, but only based on these 3 points. So that's how we do that. And this one is two-dimensional problem. For sure, in reality, we have like 1,000-dimensional problem. So line becomes like a hyperplane. The other method, probably you've heard a lot about it. And that is when people start thinking about some science fiction and so on. It's artificial neural networks. What it does, it simply has mathematical operators somewhere here in hidden layers so that it tries to match input information with desired output. And this method is used by Facebook, YouTube, and Amazon a lot because they have access to a lot of data. In science, you probably rarely see this method applied because if we have hundreds of data points, we are lucky. Another one common method is random forest algorithm. It has its own advantage. We can work with data where we have some incomplete entries or something unreliable data or so on. We use a subset of variables, subset of data to create this very common decision trees that are assembled into forest. And overall, if you want to start applying machine learning, you don't have to change your expertise. You still will be an expert in your field because most of the time, 90% of the time, you will still be doing absolutely the same thing you do every day. You'll be reading papers, compiling some tables, making conclusions about like what you see and so on. That's why I guess it's quite important to show this flowchart that tells you that 80% of your time, probably you'll be assembling and pre-processing your data in the database. Additional 10% of time you'll spend on validation if you want to do that. And you just need that tiny bit, 10% of your time and a little bit of technical skills to get into machine learning. So it's not really that complicated, especially taking into account that nowadays we have programs with graphical interface that allow users with absolutely no programming experience to start doing machine learning. And here's just a list of papers that we have published recently. And again, like each of the problems has been experimentally validated. So not so many groups are doing experimental validation of their machine learning model. Some of them are from Sandia Labs. Some of them are from Utah, from Houston. If you see people publishing a machine learning model from those places, they probably have it experimentally validated. So one of the problems is classification of crystal structures. I'm a crystallographer, so I like looking at crystal structures. The biggest problem in crystallography is just like if you have a combination of elements, would it crystallize in this type structure or this type structure? So some sort of these types of problems I'm interested in the most. Definitely what industry wants from us and what is very nice to put on grant application is prediction of physical properties. Something that also we've been working for a long time. Some of the properties that we have successfully predicted and validated are listed here. And some of other application of machine learning that I'm working right now is optimization of current devices. More specifically, organic photovoltaics for energy conversion that we have successfully optimized with machine learning. So this was like the introduction for about machine learning, and that's probably everything that you need to know about machine learning as a PI. Technical details are not provided here, but I will go through some case studies here. Some of them will be classification problems, some of them will be regression problem, just to give you sort of like an overview what it might be used for. So there will be materials problems, and probably there is a high chance that you are not working on materials, but you can look at these examples and maybe just find some similarities in terms of approach so you can apply for your type of problems. Okay, so one of the case study that I want to quickly go through is thermoelectric materials prediction. So this is the very first study that was experimentally validated in chemistry domain. It was prediction of thermoelectric properties. And this one was done with the help of informatics company, Citrin Informatics from Redwood City, California. That's why I cannot reveal all the details about the model. But I guess it's good to show the very first work in this field in materials where we have applied machine learning. So thermoelectric materials, they're materials that can be used to convert temperature gradient into electric potential, or the opposite way. If you have electric potential, you can convert it to temperature gradient. It can be used for harvesting some heat that is generated by cars, or also it can be used for some devices that are too far from sun, so they cannot harvest solar energy. So that's why they use a radioisotope thermoelectric generator. So we have created a website, which you can access by this link, and it helps you to explore all the materials reported in crystallographic databases, and all the materials, you can sort them according to what property you're interested in. Thermoelectric property in general is a combination of 4 properties: Seebeck coefficient, electrical conductivity, thermal conductivity, and band gap. That's why it's very hard to find like decent thermoelectric materials, because you need to balance like 4 properties at the same time. This database and machine learning model was created based on experimental data, and it requires only composition as an input information. So X vectors, in our case here, are properties of elements. It also allows you to put in any compound name, any formula, and it will give you an estimate of its property. So in this case, we had to set up a criteria for decent thermoelectric materials. For example, like thermal conductivity has to be less than 10 watt per meter Kelvin, so that it's considered to be like a promising thermoelectric materials. These are just a criteria that we just decided to select. And it's only using like composition to make a prediction. So these are typical graphs that shows us how accurate is the prediction. For some properties that we know a lot chemical insight about them, we understand the property better, we have very accurate prediction. For example, like the fraction of data, over 50% of them are predicted, could be predicted without any error at all. And the spread of overestimation and underestimation is quite good here. For some properties, it's quite tricky, like Seebeck coefficient is not as accurate prediction as it could be, but always prediction is better than just a random guess. So based on this, we just decided to discover a new class of thermoelectric materials. More specifically, we just noticed that there is very interesting prediction by machine learning that there is a thermoelectric material that has very high content of transition metals and other metallic components in it. And most of thermoelectric materials don't have that huge fraction of metallic elements. So we just decided to test these predictions. So there's a high confidence that our material will have very low thermal conductivity. For metallic systems, it's quite unusual, and high confidence that it has like low resistivity and so on. So when we do actual measurements of our materials, they turn to be correct. So the prediction, if we have thermal conductivity less than 10 watt per meter Kelvin, and we can see on thermal conductivity, all the measurements are less than 10 watt per meter Kelvin, and so on and so forth for other properties that we have predicted. So it works quite well. And definitely we synthesized that material, of course, very nice crystals, quite pure phase. And even that ZT value, which is figure of merit for thermoelectric materials, is not that great. It's not like revolutionarily breakthrough, but we found a new class of materials with machine learning. In other words, machine learning was used to suggest a new class of materials which basically made a suggestion outside of the box. So that is a great application of machine learning. It helps you, it can give you some suggestions that seem to be quite counterintuitive for you as for the researcher. But it tells you that probably you should go to the lab and try it. So that's what we did in this case. So the reason for low thermal conductivity is unusual environment around bismuth atom, which rattles in a cage. And overall structure looks very similar to scooterudite type structure, quite common for other thermoelectric materials, but it's a little bit distorted. That's why it would be simply overlooked by chemists because, well, it doesn't look similar at first glance, but when we analyze structure, so it was quite similar to scooterudite type structure, typical thermoelectric material application. So we can also use this model to separately predict one property. So for example, we decided to predict thermal conductivity, which has quite a good overall model quality for this type of property. So we just decided to, let's stick to ternary systems and find a system which has very high probability of low thermal conductivity, the dark red regions here. And let's just try, simply go to the lab and try this ratio of elements that was suggested. And we found like a new compound there, which we were quite surprised. And when we measure its thermal conductivity, it appears to be way below 10 watt per meter Kelvin. This is what was our prediction. So overall, you can think about machine learning also as an online tool that you can put up online, that people can come to your website and explore like different materials or just get some predictions by simply entering the formula. That was one application of machine learning model. I will show you another application of machine learning model. So this one, this is a study that I was doing during my postdoc in Houston. And we did quite an unbelievable thing. We predicted new super hard materials within half a year from starting doing this project, even that we had no clue what hardness is and nothing. We knew nothing about hardness. And within half a year, we predicted like 2 super hard materials. And on average, people who are working on targeting super hard material, they probably publish 1 super hard material a year, like Richard Kainer from UCLA and so on. So it's quite an interesting challenge to take. So can machine learning help us with targeting new super hard materials? Probably it can. So the problem with hardness is that hardness can be measured various ways. So these are the different shapes of penetrators here, which is different shapes of diamond, basically. And you try to put some load on that diamond and see how it deforms your material. So here is like the indents, the plane view of indents that the diamond tip leaves on the surface. So here is like a typical instrument setup. And here is like Vickers hardness response. It looks like a pyramid shape. Softer your material is, you will have like a larger indent. If your material is harder, you will see like a smaller indent. We just decided to stick to Vickers hardness simply because there are more measurements, more experimental data on that. And the difficulty with hardness is simply that there are different ways to measure them. At least 5 of them are listed here. But unfortunately, you cannot directly convert one scale to another scale. You can think about it as measuring temperature in Fahrenheit and Celsius. Of course, there is a formula that gives you like approximate conversion, but there is no like direct conversion from one scale to another scale. And that's the difficulty. So what do we know about hardness? That hardness is related to elastic moduli, schematically shown here, bulk and shear moduli. And we also know that its proportional hardness is proportional to bulk and shear modulus. We don't know the actual ratio between them. We cannot like find the exact relationship between them, but we know that super hard materials, they have high bulk and high shear modulus. So just to summarize it for you, hardness is a combination of properties. So that's why we cannot target it directly, but we can screen for hardness. We can use what we call proxy properties, bulk and shear modulus, to find superhard materials. So, for example, we know that all superhard materials are also ultra incompressible, which is a good sign for us. So we will try to find materials with very high bulk and very high shear modulus. Very likely it will be superhard. There was a try a couple of years ago, no, probably a couple of decades ago, to correlate hardness with bulk and shear modulus. And you can see it works very well, correlation, if we take this publication data from a very long time ago. But these numbers, these coefficients, they are not random, but they're sort of fudging. You just take like hardness and you try to correlate with B and G, and it doesn't work very well for some cases. When we try to test it experimentally, you can see that sometimes they differ more than 100% of values. For some materials, we can see the qualitative hardness to bulk and shear modulus relationship, but in some materials, they are not even qualitative. So in terms of quantities, quantitatively, they are a way off. So that's why we need a new formula that correlates hardness to bulk and shear modulus. Anyway, for our prediction, we use the data, more specifically over 2,000 compounds generated by materials project, because these properties could be calculated with DFT. And we had 160 descriptors over X vector. And we can generate like a huge number of bulk and shear modulus in very short time. And this is not on computer cluster, it's just on a laptop. You can do it. More specifically about features, the X vector. So these are the properties that we have considered, 150 of them. And we require feature selection because we need to make sure that we remove features that don't put anything useful in our model. That's why we have all features and their potential usability, their potential importance, I would say, in a model by black bars. And after feature selection, we see the features that were selected after genomic algorithm, after feature selection. So some of them were selected, some of them were not selected, and so on. So why feature selection is important? When we look at the correlation between training set, the one that we input the data, and prediction, ideally they all should be, if you have good model, along this line. And we kind of see it here, but we can definitely make a better model. So just to make sure that we align like as many as possible samples along this line, which has a perfect correlation between prediction and result. So if we reduce number of variables by only 4 variables here, we can see that some points come closer to this line, which is a good sign. Especially we worried too much about hexagonal boron nitride, which initially had quite a bad prediction. If we do feature selection with other methods, we can get even better prediction. And the final model that we have published looks like that, the blue one, which has only 60 variables. So it's like 2 times less variables that we started with. And we have like a decent prediction of bulk modulus. So data redundancy could be an issue, so we just need to deal with it by feature selection. So this is the final results. We have bulk modulus, we have shear modulus prediction. Shear modulus doesn't predict very well. Well, maybe because we don't understand a lot of chemistry that is involved into shear modulus. But anyway, this prediction is better than just having nothing or random guess. And we did experiment at HPCAD. So Dr. Miyagi from University of Utah helped us with that to experimentally figure out what is the bulk modulus of our material. So the experiment shows 370 GPa, which is in very good agreement with machine learning within the standard deviation. But with DFT theory calculation, it is 20% off. So this just simply shows experimental validation of bulk modulus prediction and how accurate it is. So next, we want to screen for superhard materials. We know that it should have high bulk and high shear modulus, so we focus on this part of the diagram, bulk versus shear. We can see some common superhard materials listed here. And we also find the ternary and quaternary compounds, which have like the highest bulk and shear modulus. So we consider them to be new superhard materials. In fact, these are our candidates. The main problem you see right away that they have atomic mixing, which makes them difficult to be computed with DFT to predict their bulk and shear modulus. But with machine learning, it's not an issue, so we can deal with it. Definitely experimentally, we have made the compound. Here's the structure. It's pure. It forms right away. We don't need to anneal it or anything like that. We do the measurements, and they exceed 40 GPa threshold to be considered super hard materials. It's definitely harder than steel. It's harder than quartz, topaz, and corundum also. So these materials are super hard. In other words, these materials, in terms of hardness, are compared to recently reported rhenium borate and tungsten borate materials. And the best thing, it doesn't require high pressure and high temperature to be synthesized. It can be made just with arc melter right away. Definitely, we cannot reach diamond, of course, but it wasn't our goal. Our goal was just to develop super hard materials, and we found it. Yeah, that's always super hard materials. And I probably want to briefly mention to you prediction of crystal structures. So crystal structures can be predicted. Well, it's very hard to tell if they can be predicted or not, but people have tried to figure out some geometrical rules like Linus Pauling that he did like many, many decades ago. And also people try to predict crystal structure from first principles. And you can see from publication from 1994, most of people just think that it's impossible to predict crystal structures. Of course, it is possible right now, and we all are using so many algorithms nowadays that help us to predict crystal structures like Calypso, USPEC, and IRSS algorithm, and many others. So still, these algorithms have some issues with F electron compounds, and sometimes with magnetic D element compounds, and so on. So we just try to predict crystal structure. We are not talking about design here, because there's a very nice paper about that our design is just an illusion. So we can design a kettle this way, that we talk about things that we can design, but we cannot design a structure. So the author claims that we only can, we are just explorers here. We can just only find out if the structure will form or will not form in this particular arrangement of atoms. That's that's what we call structure prediction, actually, if it would form this structure or not. And back in the 60s, people did, actually it was in 80s, people did try to figure out if there are clusters of structures based on only two parameters. Here's pseudopotential radii, difference in electronegativity. People try to draw some clusters of compounds. And it gets quite ridiculous when you have like 40 structures, 50 structures, nearly impossible to read anything on this diagram. I tried to do it myself back in 2013, one of the publications right here. So I tried to consider like two parameters and try to find clusters. Well, with machine learning, we can deal with like 50 variables or so and plot it on a principal component space and try to search for some clusters of compounds. So first, we tried to predict phases that have the simplest binary stoichiometry, equiatomic ratio 1:1. These compounds are important because they were used to develop some basic chemistry concepts. For example, like electronegativity scale is based on binary compounds, and so on and so forth. And valency, the very chemical properties, also based on 1:1 compounds. These are also very cool materials. Some of them can be used as refractory materials. Some of them are good semiconductors and so on. So if we look at crystal structure, they all form clusters of structures that can be summarized in structure types. Structure types are simply atomic arrangement, and it's named unique atomic arrangement. It's named by the structure that was first found in this structure type. For example, cesium chloride type structure, sodium chloride type structure have the same ratio of elements, but different structures for sure. And in total, we have like a lot of structures there. But for machine learning, for statistical purpose, we only select crystal structures that have enough representative, for example, like 30 representative from each class. And then we try to predict them. This is a prediction of cesium chloride type structure compounds that are red circles right here. If they're really cesium chloride type structures, they will cluster somewhere around 100% probability. Everything that is not cesium chloride type structure should be here at the bottom. So this way we predicted experimentally validated with a new binary equiatomic compound, rhodium cadmium, but which is more important, we can also flag some suspicious entries and unreliable data. For example, copper fluoride, which stands out right here, even Wikipedia knows that its existence is uncertain. So this compound was reported in 1930, but when people tried to reproduce the experiment, they couldn't make this compound in this particular type structure, which is a very helpful tool. So machine learning helps us to flag suspicious entries and weed out some unreliable reports. And the very last, just take like 5 minutes here to finish, was structure prediction. We tried to go to a little bit more complicated cases, ABC, equiatomic, ternary compounds. And most of them have the issue which is called polymorphism. Definitely, the structures can be arranged into one type structure or another type structure, depending on conditions. These structures are related through the common parent structure. That's why people try to study what is the reason for polymorphism. Why in some cases we have one type structure, in another case we have a different type structure. So these are predictions of crystal structures and their statistics for titanium nickel silicide type structure, shown right here, and zirconium nickel aluminum type structure, shown right here. So the compounds can be predicted quite well, but there are also some of them that have probability neither 100% nor 0%, somewhere in between. And it can mean two things. First, it can mean that our model is not very reliable. Or second thing, it can mean probably the reports were not right. That's another possibility. And the third one is that it means something about chemistry. Maybe these compounds that have like intermediate probability can form two-type structures. And we try to plot all of them here. So here are their probabilities. They are sorted by probabilities. And there's also a region when we have some what is called intermediate probabilities. So, and our claim was, so maybe these compounds are the compounds that can simply coexist at the same conditions. It definitely contradicts some traditional thermodynamics, but at the same time, we know that it's not only thermodynamics that is involved in structure formation, we also have kinetics. And it might be the case that formation of one phase is kinetically suppressed, so we can have and observe two phases at the same time. And in fact, all the compounds listed here in gray region, they were found to exist at exactly the same conditions, synthesis conditions. Well, definitely we had to test it somehow. That's why we did synthesis. And it's very good that we have evidence right away when we look at the sample and it has two different colors to it. And two different colors correspond to two different phases. And in fact, we have a combination of titanium iron phosphide in two different type structures in one sample. In other words, here in this study, machine learning helped us to identify phases that can potentially coexist in one sample. Okay, so here's just a summary of the project. So if any other project might be of your interest, for example, like organic photovoltaics or energy storage, energy conversion, or any other properties that you see listed here, just feel free to ask me more questions about it later. And again, I just want to mention it once again. So experimental validation of machine learning model is super important. So last year, there were over 2,000 publications with tag machine learning and either chemistry or materials. But only 5 of them were experimentally validated, and 3 of them were my publications. So it's a huge issue in machine learning community that you need to validate your prediction. If you can't validate your prediction, it has no value at all. And I just want to thank you for your attention and thank my group and my colleagues from other institutions to help me with this project. And thank you for your attention once again, and I will be happy to answer your questions.
Thank you. That was a beautiful introduction. I really enjoyed, particularly the first part, learning about the details of machine learning and looking a nice preamble to tomorrow. Let me get a question back here from Bob.
Thank you. That was really a wonderful overview. So one of the things that struck me and has struck us in our work is when you said 80% of the time is spent preparing your data resources. And so I wonder if you could comment on the possibility of using some of these techniques in AI and perhaps machine learning to build our databases from the literature, something that's been tried, for example, in the Geo Deep Dive initiative at Wisconsin.
Yeah, absolutely. It's basically is data mining, just getting some useful data from the papers into a very well-structured database, and the efforts are undergoing, of course. So there are also algorithms, and that's more about AI and language-related AI, but people are already succeeded in compiling a database based on experimental sections. Because when we write experimental section, and if we work on this in the same area and write experimental section, it sounds more or less the same from paper to paper. For example, like we prepared sample by arc melting at this temperature for that many days. We collected data at this diffractometer for that long and so on. So all this data is very well structured, and for AI there is absolutely no issue of extracting it from the paper. The problem is conclusion section, because conclusion, it requires making some decision. And making decisions, so sometimes there are papers with open conclusions, so you can just make conclusion yourself. Sometimes there are some questionable conclusions published by people. So this is like the part of the manuscripts that is harder and harder to extract the data from. But you're right, there are also so many initiatives, but these initiatives, they mainly focus on language-related AI to extract the data more efficiently.
I was wondering if you could expand on the selection or the optimization of which data points are used for training and which ones are used for validation with these kind of small number sample sets?
Yes. So let me just go back to that slide. I don't remember the number. Do you remember the number by chance? Yeah, the slide.
More generally, you showed a lot of those plots where you had the sort of validation on the left and the training on the left.
So yeah, let's just stick to this slide. Yes, so it's a good question, what we put in training set, what we put in validation. Because some researchers can be very biased and split the data themselves. They can put like better data in training set so they get a better statistics and so on. So to avoid that, we use we do a training set and validation on different subsets of data. So our standard procedure is having this step done 10 times. So it randomly selects subset of variables for training, subset for validation. And if the results are close to each other, that's how we make a conclusion that, yes, it probably works well.
Okay, so you just run the whole process, randomly select 2/3 of it for training and then the other third.
There are,
do that 10 times.
yes, yes. And when I say randomly, it just simply my way to generalize the way to split the data, because there are different ways of them. There is method which is called Venetian blinds that doesn't take the data randomly. It just takes a subset of your data, like let's say like block of 10 data points, then block of 10 data points go to training, block of 10 data points go to validation and so on. But it depends on your data, because if your data is very well randomized, it will work. If it's not randomized, if it's sorted alphabetically, then it's not going to work. Because if you sort like chemical compounds alphabetically, you'll probably have like silver compounds first, then you have actinium compounds, and so on from A to Z. And that's why you can't take a block of data, because, for example, in your training set, you will have all compounds with silver and no other compounds, no diversity in your compounds, and that might be an issue. So it depends on your data, how it was prepared. But I will show you more about the split of data tomorrow for sure, but there's definitely ways to make sure that we don't cherry pick our compounds for training set.
If you don't have any data at all in some specific example, then can you use extrapolations from some other properties and predict new compounds? For example, let's say we want to discover some compounds in high pressure, high temperature regime, but there is no such compound existing. But using the properties at ambient pressure or some other axes, can you predict materials in high pressure, high temperature, for example?
Yeah, if I get you right, so you probably are saying something about proxy properties. And proxy properties are super helpful for us, especially when we want to predict something that we don't really understand how it works. Let's say hardness, it's very intuitive for us what is hardness, but in fact it is a combination of properties. It's not just only one property. It's always like it has many components to it, like it depends on microstructure, it depends if hardness is measured in nanoregime or microregime, it depends of if it has like phase mixing, it depends if it has grain boundaries. That's why it's like a very complex properties. That's why specifically for hardness we use proxy properties, what we call. We know that somehow one property is related to the property that we are targeting to. So we try to predict this class of compounds by first predicting proxy properties. It's a very common approach. For example, what we did recently was prediction of new phosphor materials, because photoluminescence is also quite a complex topic. And what people notice that usually compounds with high photoluminescence yield, they also have high Debye temperature. You cannot directly relate one to another, and some reviewers can say that these properties are completely unrelated to each other. But in fact, if we statistically can see that there is a correlation between high Debye temperature and high yield of phosphor materials, so we definitely can predict a material by predicting Debye temperature first. So yeah, answering your question, of course, using proxy property is the way, especially for very complex materials.
So as I walk down to Zach, if you look at your Thermoelectrics database that you did with citrine, and you can establish thermal conductivity just based on composition, what happens if you put in the element C?
I haven't tried that.
Because on one hand, you have diamond, which has the highest thermal conductivity of any material known. On the other hand, you have amorphous carbon glass, which has a very low thermal conductivity. So I'm wondering how the model would handle that.
So I don't actually remember what we did, but I'm afraid that we try to avoid working with elements for that specific reason. So that's another question. So when we put a database of elemental properties, we need to select one of them. And which one are we going to select, graphite or diamond? I would stick to graphite properties because it's thermodynamically stable phase. But you're right, for some elements, especially in terms of prediction, it's very hard to tell. And I guess it will just blow up our model. It will just ruin it. Unfortunately, it's not going to work. That's why I guess we did something like avoiding elements for that specific reason.
I have a philosophical question. You said your philosophy is to find an experimentalist to test your prediction. Why not have someone run DFT calculations to test your predictions? Okay.
Yeah, you're absolutely right. So my philosophy is doing experiment, but I am the experimentalist. So I'm not the guy who's sitting like at the computer the whole day. No, I still have that excitement going to the lab and doing it myself, of course.
Why not do DFT calculations?
Yes, we do DFT, and we do it on a regular basis. Yes, we do DFT. The only problem is DFT cannot solve all the problems, and it has a lot of issues with F elements, some D elements. It has a lot of issues with large systems when you have thousands of atoms. Maybe it's not even an issue, but it will take forever to calculate it. So also there is an issue if you have low symmetry. So what my philosophy is, in addition to that, we don't try to compete with DFT people. We try to solve the problems that DFT is having problems with right now. And the very problem we are trying to solve is is atomic mixing or atomic deficiency at some positions, which DFT will definitely have a problem with. But there are some codes that can deal with the deficiency, not going to supercell approach if you're interested in that. There's like approach called CPA, and it's implemented in Akai KKR code, which can help you to calculate like very, very tiny deficiency, like less than 1% deficiency in one position or very small mixing. But unfortunately, this code is, documentation for this code is written in Japanese. That's why you need to use Google Translate to figure out how to use it. But yeah, people try to overcome that problem. But again, I'm just repeating myself here, but our philosophy is not competing with DFT people. We really appreciate their work. We just try to complement their work.
All right, well, let's continue the discussion at lunch. Thank Anton one more time.
Thank you.
And if you didn't sign up for the classes tomorrow and you're interested to come, let me know.